The battery most homeowners are being sold today was never designed for the problem an off-grid house actually faces. Lithium batteries are excellent when you need a lot of power from a compact package. That is why they belong in electric cars, phones, power tools, and portable equipment. But your house is not moving. It is not limited by the weight of the battery, and during a serious outage, your biggest concern is not how quickly the battery can discharge. It is whether you will still have electricity on the third or fourth night. That is where a much older battery chemistry becomes interesting. It stores energy by allowing iron to rust and then reversing that process during charging. One side of the battery is made from iron. The other draws oxygen from the surrounding air. There is no cobalt cathode, no nickel-rich chemistry, and no need to package every unit into a thin, lightweight box. It is called an iron-air battery, and several companies now believe it could become one of the least expensive ways to store renewable energy for days instead of hours. But there is a catch, and it is a major one. This is not a miracle battery you can safely build from a bucket of steel wool and use to power your house. The real systems require engineered air electrodes, controlled electrolytes, power electronics, ventilation, monitoring, and certified safety equipment. The chemistry may sound simple, but turning it into dependable household power is not. So why should anyone interested in off-grid living care about it? Because iron-air technology exposes a weakness in the way most home energy systems are currently designed. We have been trying to solve a long-duration problem with batteries optimized for short-duration performance. By the end of this video, you will understand how iron-air storage works, why it could eventually cost far less than lithium, what it can and cannot do, and how its basic design philosophy can improve an off-grid system you are planning today. And stay with me, because the biggest lesson is not about iron or lithium. It is about the mistake homeowners make before they buy either one. Let us begin with what actually happens inside the battery. When an iron air cell discharges, oxygen from the air participates in a chemical reaction with iron. The iron oxidizes, which is another way of saying it rusts. During that reaction, electrons are released and sent through an external circuit where they can perform useful work. When electricity is supplied during charging, the reaction is pushed in the opposite direction. The iron oxide is converted back toward metallic iron, and the cell is prepared to discharge again. In simple terms, the battery stores energy by rusting iron and charges by reversing the rust. That sounds almost too basic to be useful, but simplicity is part of the attraction. Iron is abundant, widely available, and inexpensive compared with many of the refined materials used in modern lithium-ion cells. An iron-air system also uses oxygen from the atmosphere as part of its electrochemical reaction. Instead of carrying all the active material inside a sealed cell, the air electrode interacts with oxygen entering from outside the battery. That can reduce material costs, but it introduces a difficult engineering problem. The air electrode has to admit oxygen while controlling moisture, contaminants, electrolyte movement, and carbon dioxide exposure. It must continue doing that through thousands of cycles without clogging or degrading. This is the first open loop worth remembering. The iron is cheap. The part that breathes is not simple. Modern iron-air developers are not merely placing iron in a container and waiting for electricity to appear. They are engineering systems in which air, liquid electrolyte, iron electrodes, membranes, pumps, sensors, and power controls all have to operate together. The potential payoff is long-duration storage. Most residential lithium battery systems are sold around overnight backup or short utility outages. Depending on the home's consumption and the number of batteries installed, they may provide several hours or perhaps a day of useful power. That can be enough for common outages, but it becomes a problem during several days of poor solar production. Imagine a rural house in January. The sky stays overcast for 3 days, the temperature falls, and snow partly covers the array. Your solar panels are producing a fraction of their normal output, but the well pump, refrigerator, freezer, lights, communications equipment, and heating controls still need electricity. A battery designed mainly to cover one evening may be depleted before the weather clears. A long-duration battery is designed around a different goal. Instead of delivering the maximum possible power from the smallest package, it sacrifices compactness and efficiency in exchange for lower material cost and much longer discharge time. This is where iron air becomes fundamentally different from lithium. Lithium-ion batteries are generally highly efficient. Most of the electricity used to charge them can later be recovered, although some energy is always lost through conversion, heat, and supporting equipment. Iron air systems are expected to return a smaller percentage of the energy used to charge them. Reversing the formation of iron oxide requires energy, and additional losses occur through the air electrode and other components. At first, that sounds like a fatal weakness. Why would anyone install a battery that wastes more electricity? Because efficiency is only one part of the calculation. Suppose you have excess solar power at midday that would otherwise be curtailed, exported at a poor rate, or simply unused because your batteries are already full. Storing some of that surplus at lower efficiency may still be valuable if the storage system is inexpensive enough and can carry your critical loads through several dark days. This is the same reason a homestead may keep a large water tank, even though a smaller pressure vessel is more convenient. The tank is bulky, but it holds a resource you may need later. Long-duration storage is less concerned with elegance and more concerned with endurance. Now here is where many homeowners misunderstand the comparison. An iron air battery would not necessarily replace every lithium battery. The two technologies perform different jobs. Lithium is strong at responding quickly, handling sudden power demands, and delivering substantial current from a relatively small system. Those qualities matter when an air conditioner compressor, well pump, or power tool starts. Iron air is better suited to releasing energy slowly over a longer period. That makes it a potential reserve for refrigeration, lighting, controls, communication equipment, and other steady loads during an extended outage. A future off-grid system may use both. A smaller lithium bank could absorb rapid changes and handle startup surges. A larger iron air bank could provide lower power energy over several days. Solar would recharge both when conditions allowed, while a generator might remain available for unusual weather or maintenance emergencies. That hybrid arrangement reveals the larger principle. You should not ask one battery to perform every job. This next part is the one thing I would tell anyone before spending money on home storage. Measure your loads before choosing your chemistry. Homeowners often begin with a product. They see a battery advertised as having 10 or 15 kilowatt hours of capacity and ask whether one unit will run the house. That question cannot be answered without knowing what the house consumes. An efficient refrigerator, a few lights, a modem, and heating controls may operate for a long time on a modest battery. Add central air conditioning, an electric water heater, an electric range, a clothes dryer, and a deep well pump, and the same battery can be exhausted quickly. You need to know two different numbers. The first is energy, measured in kilowatt hours. This determines how long the system can operate. The second is power, measured in kilowatts. This determines how much equipment can operate at the same time and whether the inverter can handle startup surges. A battery may contain enough energy to run a well pump repeatedly throughout the day, but still be unable to provide the pump's momentary startup demand. Another system may deliver enormous power for a few minutes, yet lack enough stored energy to last through the night. That is why the phrase whole home battery can be misleading. The battery may be connected to the whole house, but it does not create unlimited energy. A competent off-grid plan divides the home into load priorities. The first group includes equipment that must continue operating: refrigeration, water, medical devices, communications, basic lighting, heating controls, and perhaps one efficient heating or cooling zone. The second group includes loads that can be used selectively, such as a microwave, washing machine, workshop circuit, or small air conditioner. The final group includes equipment that should usually remain off during an extended outage: electric resistance heating, large water heaters, clothes dryers, pool heaters, and other heavy loads. Reducing consumption is almost always cheaper than adding enough battery capacity to support every appliance without restraint. This is also why iron air storage is likely to appear first at utility and commercial scale rather than inside ordinary homes. Large installations have space. They can use rows of heavy battery modules without worrying about fitting them onto a garage wall. They also have trained operators, engineered ventilation, fire control plans, monitoring systems, and the ability to service individual components. Weight is not a major disadvantage when the battery remains permanently installed on a concrete foundation. At residential scale, however, certification matters. Any system connected to a home must meet electrical, building, and fire requirements. It needs compatible inverters, disconnects, overcurrent protection, proper grounding, isolation from the utility during an outage, and equipment approved for the intended installation. This is where online claims about homemade iron air batteries become dangerous. A small experimental cell may be able to illuminate an LED or produce a measurable voltage on a workbench. That does not make it suitable for powering a refrigerator, connecting to an inverter, or being installed beside a family's home. Some alkaline electrolytes used in experimental batteries are strongly corrosive. Charging can also produce gases that require controlled ventilation. Improvised wiring may overheat, and a bank of many cells introduces far more energy and risk than a single demonstration. There is an enormous distance between proving a chemical reaction and building a dependable energy storage system. Respecting that distance is not an argument against self-reliance. It is what responsible self-reliance looks like. So where does iron air fit into the future? Its strongest role may be storing energy for the periods when wind and solar production remain low for several days. Lithium batteries can smooth short fluctuations and shift afternoon solar into the evening. Iron air or other long-duration technologies could cover the longer gaps. For an individual homestead, the lesson is to design in layers. Begin by reducing the home's load. Improve insulation, control air leakage, shade windows, use efficient refrigeration, and avoid relying on resistance heating wherever practical. Next, size the solar array for realistic winter production rather than impressive summer numbers. A system that looks oversized in June may be barely adequate in December. Then install enough certified battery capacity to cover the normal overnight period and common outages. Finally, add a second source of resilience. That may be a generator, stored fuel, thermal storage, wood heat, additional water capacity, or eventually a commercially approved long-duration battery. The strongest off-grid properties do not depend on one perfect machine. They use several ordinary systems that support one another. That is the bigger promise behind iron air technology. It is not that a handful of rusty metal will replace a professionally engineered home battery tomorrow. It is that energy storage may not always need to be built from scarce, expensive materials or replaced on the same schedule as today's lithium products. A stationary battery is allowed to be heavy. It is allowed to be large. It is allowed to charge slowly. What it cannot be is unreliable when the weather turns bad and the grid stays down. Iron air developers are betting that homeowners, utilities, and rural communities will eventually value duration more than compact packaging. Whether the technology reaches ordinary houses will depend on its real cost, efficiency, maintenance requirements, certification, and performance outside controlled demonstrations. Those questions are not settled yet, but the underlying idea is sound enough to change how we think about backup power. The best battery is not automatically the one with the highest energy density. It is the one that matches the job, survives the environment, and provides power for the length of time you actually need it. So here is the question I would ask before buying any home battery. Are you preparing for a 4-hour outage, one night without the grid, or an entire week of poor weather? Those are three completely different problems, and they should not be solved with the same system. Tell me in the comments how long you want your home to remain operational without utility power, and which load you consider absolutely non-negotiable. Is it the well pump, the freezer, the air conditioner, medical equipment, or something else? In the next video, we will take a real household load list and calculate how much solar, battery storage, and backup generation it would require to remain functional for 7 full days. Because choosing the battery comes later, the first step is deciding exactly what must keep running when everything else goes dark.